septième credo septum.
Okay, good morning, everybody. My name is Satyanto Saptomo. I am from Bogor Agricultural University, or now we rebranded as UPP University. And today I'd like to present our implementation of subsurface perforated pipe networks to improve what paddy field water management. Okay, rice fields are the agricultural lands that have undergone conversion in Indonesia, especially from rice field to non-rice field, mostly is to housing. So increasing the values of the field for so to have such more economic value of products, or to increase at the multifunctional can be one of the incentives to reduce the budget. To and the, to produce high value product compared to rice from cultivation, conventional cultivation might require specific management. So it is.
Microphone, please.
Oh,
Hold.
hold. Okay. So to produce high value products compared to rice from cultivation, conventional cultivation, often need a specific requirement of specific water management system. Then if we can do the much more, if water efficient subsurface irrigation, it can increase resilience to prolonged dry season and increase water productivity, of course. And so if we also can well manage the agricultural water, it also can contribute to control greenhouse gases emission. So then the subsurface water management system can be a solution which allow flexibility in irrigation and enable the paddy field to function as either wetland or dry land. You can plant uh, rice or other non-water flooding crops, something like that. And also lately, I think that adding the function of delayed water release through subsurface water management system could contribute to delay the surface runoff. So, in somewhat, we can contribute to delay the decrease the uh, potential of flood at the downstream. So this was my presentation last year, and Professor Mizuguchi asked me what I'm going to answer today, and this is what we are going to do. So last time we developed a model in laboratory, and now we want to move it to experimental plot, but about 300 meter square in area. But of course, uh, for now we haven't finished the automation part yet, but we just bring it out to the field. The problem is when we want to make the bigger size of land with subsurface irrigation and drainage system. It's a lot of things to think about. Sorry. So the objective is first we want to develop a land with subsurface management system, and we observe the variation of water table during irrigation and drainage, and we observe the distribution of water table over the field. Now, this is the biggest problem in Indonesia because basically we use the Japanese technology of sheet pipe, which usually we will need a heavy machinery to install the sheet pipe. So we think how we can make this, how can we do this without machinery at the place where we can use, even the machinery cannot enter. So we think of the manual ways and the way to. So at first we dug the canal and we laid the pipe, and we have to bury it with something that can avoid clogging. So we use reinforced sand with special techniques we developed at our university, and this done like this. This is sand, but it's hardened without uh, without sacrificing the permeability. So then the land is ready for preparation and cultivation. So this is the land. This is the pipe networks. This is the inlet of irrigation. So the water will go through underneath to the perforated pipes, and these are the drainage. The location in Bogor, the size is 12 times 25 meters. This is the bigger one. Sorry, is it still in Indonesia? I hope you can understand. I want to show how we installed the pipe. So this is the pipe, and we buried it with kind of, we call it MCP sand. I will explain later if anyone interested. So we put the pipe about 40 centimeters, but we add about, oh sorry, we the canal is 50 centimeters, but we adding up the reinforced sand up to 20 centimeters. So basically it is 30 centimeters under the surface. So we try to do a simple monitoring observation. At first, the water table monitoring. Well, actually, only this monitoring, but we do it with two approach. At first, we use the sensors, water table, water level sensors based on LoRa technology. So, the technology of LoRa itself is not directly related to the research. We just use it because it is simple, and we can avoid, straight putting cables around the field. And also we did the observation manually at 9 points. This is hourly for 1 full days and one daily for 1 week. So this is the setting of this is the manual measure one. This is the sensors. From the side you can see this. So we actually using this principle of communicating vessels to irrigate, to give water underneath with certain hydraulic head. So hopefully it will control the water table inside the soil. Okay, this is another. Well, it's not. This is what we use, but maybe I'm not going to explain this in detail. And this is the result. At first, we compare the water level at the inlet of irrigation. This is the inlet of irrigation, and 40 is the soil surface. And if you see this, this means the land is flooding because not because the subsurface irrigation, but overflow because we put a hole for overflow irrigation at the irrigation inlet reservoir. So anyway, we observe the water level here. This is 30, and we look for when this is the water table at the middle of the land. So it requires about 190 minutes to reach from zero, not zero, 15 to 30 centimeters. So it requires somewhat significant time. And if we look at full sensor reading at the middle of this, at the center of the field, we can get increase about 25 centimeters within, I think it's roughly 250 minutes from 50, yeah. So 25 centimeters about 250 minutes. And this is the distribution of water table. This is 1 day. So this is by the end. This is the first day, first measurement up to so we can see the water flowing, yeah, from we in this case we close the drainage, okay, and then we try to drainage. At first we saturated the plant the field, so and then we open the drainage the drainage outlets, and this is the decreasing of the water table at the center of the field. So roughly for 15 centimeters, it required this is 3 hours, right? 150 minutes, and this is the distribution of the water table. Uh, so we can see, yeah, the water flowing over there. The brown is the lower water level, okay, and this is when we observe about 7 days. Yeah, I think somewhat is like we expected, like we was expected, but we still need confirmation. Okay, the water level at the center of the field reaches on the same level at the inlet, about 30 centimeters from the datum, about 3 hours, and the distribution water distribution in the field is uniform based on manual measurements of water level at 9 observation points. I think we can control somewhat the rainfall runoff to the subsurface drainage. So we close the surface drainage and let the water go through through the subsurface flow. And if we refer to the last drainage observation, water table decrease of elevation, it will can delay about 3 hours. Maybe it's enough to uh, contribute to the decrease of runoff. And this transformation hopefully can create productive land for various products and cultivation, also functioning as water retention area, showing how agricultural land can also be innovatively modified to enhance its efficiency, productivity, resilience to climate change, and also hopefully it will have ecological function. So this is one we just have to season planting up to now. This is paddy, rice. This is corn. Can you see no water at the surface? But beneath there might be much water. Okay, this is a conclusion for this preliminary. This actually just a preliminary study for our case. We will continue this for upcoming maybe 2 or 3 years. The land, we have developed the land with subsurface management system, and the water table during the irrigation and drainage requires time to increase and to decrease. For instance, for distance 25 meters to increase water table at the center up to the same level with the inlet requires about 3 hours, and the distribution of water table over the field has been observed, and it looks uniform for me, but it requires further analysis. I think that's all. Thank you very much.
Thank you. And please let me know that if you have any questions and comments for speakers. I have one quick question. What is a major benefit that farmers can have from using this kind of technologies? So definitely looks like you can save water, but what is the direct benefit that the farmers can have?
Okay, of course. According to my experience and learning from the past experience from the Japanese side, at first, this kind of technology can help with aeration of the field, especially clogging field, not clogging, waterlogged field that should be used for example, soybeans, something like that. So, but in my case, we are thinking how to increase the values of the paddy field. So they not only can uh, plant rice, but also whenever they want to plant higher economic value products, they can do that by controlling the water, not at the flooding level, but also from beneath. Also, I hope it can increase the resiliency to climate change.
Thank you. Any other questions? The speaker. Okay, let's move on. And thank you again for your And our next speaker is Mr. Sengsan.